Hopefully the first one is pretty straightforward. Yeah? This product here. How we do? Hydroboration followed by oxidation, magic step. I noticed it said no need to consider stereochemistry. I didn't realize that was up there. So if you just had methyl here, OH there, I'll have to kind of correct. But you definitely need to know that this methyl and the OH are going to be trans, right? Plus an enantiomer. Because this compound has an enantiomer. You're going to get both. A little free information. Don't tell anybody I told you this. But all the reactions we're doing right now are going to also give an enantiomer when possible. That is, they're not enantioselective. If you only get one enantiomer, not the other, that would be enantioselective. None of the reactions we're doing right now for test 2 are enantioselective. So, if you get this, you got to have the enantiomer. The enantiomer would also be trans, right? How do we do? I believe it's the second one, yeah? The OH is going to be on the more substituted carbon because that's where the carbocation would have been if it had formed. It's also the carbon that takes on more partial positive in the water, which attacks the chloronium ion. Yeah? All that mechanistic thinking. The one that's going to give off the most heat is going to be the one that's least stable. The one that's least stable is the monosubstituted. Contains the most potential energy. Correct? Which one did you put?
The most.
The one that contains the less heat?
Yeah.
Heat of hydrogenation, that's the heat that's given off. Written as positive, you can call it a heat of hydrogenation. Written as negative, you can call it delta H. Which one is not stereogenic? The one circled? The one circled has no E or Z. No E or Z, right? All the others are either E or Z. How do we do? Questions? Mechanism. Alkyne attacks H+, provided by the sulfuric acid, strong acid, right? Plus the H+. Make cation here, correct? Obviously, methanol does not attack here. That does not give that product. It needs to attack here. Well, do an alkyl shift. Put another methyl over here. This gives an isopropyl group here. There's still an undrawn H there, yeah? I just didn't draw it anymore. Cation here. Now the nucleophile methanol. These electrons attack here. Bond now made. One lone pair left. Positive charge. We have to lose an H. This, again, you don't have to show that out. I usually just show that condensed. Let you get away with that. The anion takes the H, electrons here, we get product, and we reform H2SO4, which was actually a catalyst here. You just try to react this with methanol, it won't react, but you have to include the acid catalyst. How we do? Okay, so this is maybe your first mechanism. There'll be plenty of mechanisms going forward. There'll be mechanisms on the test. There probably will be multiple mechanism questions on the test. There'll be predicted products on the test. There'll be a short answer, like in the middle there on the test. Question?
If we use H3O plus instead of the HSO4,
What'd you say?
if we use H3O plus instead of the H2O4, would you still count it?
What do you mean H3O plus? Used it how?
Take the
I mean,
H off.
Yeah, just instead of putting the
You mean
H2O4,
use water instead of this?
Yeah, water. And then like so that
Yes, you
it
can use
forms-
water because sulfuric is an aqueous acid.
So you would still count it.
Yes. That's actually strictly more correct. I like to reform the actual acid. Okay, this will be posted upstairs. See how you're doing. Test on Monday, yeah? Okay. Here we go. Lab today and tomorrow. You'll be turning in your unknown lab report. Okay. Today at halftime, I'll give you back the Tuesday, Thursday lab report. Today in lab, tomorrow we're doing bromination of transtilbene. Yeah? Any questions about that lab? Be our first synthesis, making a new compound. Hopefully that'll be a little interesting, fun. Mainly going forward, you'll primarily be doing synthesis in organic 1 and organic 2. Doing reactions, making new compounds, purifying the product, and then proving two things. Proving that it's pure and proving the identity. That is, did I make what I'm supposed to make as drawn on the paper? How do you do such? Questions about lab today? Okay, I think we'll meet here in this room each day. Have a little discussion. Okay, we'll probably get into the alkyne chemistry today. Alkyne handout, we have the stereochemistry, one you printed, and also the blue. We also have miscellaneous things that we need to go back and look at in the alkene handout, in the thermodynamics handout. Okay. Questions about stereochemistry before we get going? Question? Loud and proud. Question.
How do you determine the priority group if the constituents are the same, like pretty much all the way around on the hydrocarbon?
Well, you said two different things. First you said same, and then you said pretty much. So are they the same or not?
They're the same. The same constituents on the hydrocarbons.
If they're the same, then you can't, there's no way to determine it. So so I don't quite understand your question. I think you mean they're similar. Okay, I have to see what you're talking about.
Well,
Do you have is it a particular question?
well, I guess on this one right here, number 2, like I feel like I can't determine the priority group in order to.
You mean here, you can't do RS?
I guess do okay.
Right, the structure here?
Yes, that's the structure.
Okay, well the reason you can't do RS there is because there's no stereochemistry shown. I mean, is the OH forward or back? It's not shown, it's shown generically here. You can't determine it, it's shown generically. Sometimes we show structures just generically. Is that the problem?
I guess I haven't fully formed my question yet.
Okay. Well, yeah, you can't do R and S here. That is a chiral carbon. And it does two different configurations around that. But the two ain't shown here. This is just a generic representation without showing the stereochemistry. Now the question is, if we look up here, it says show them. Show the stereoisomers, the particular ones. And we can show them. And I like to draw them sort of like we drew the ones above. Okay. Let's do here. Boom, boom, boom. Above. What do we do with the OH first? Bold. And the chlorine was what on the first one? Bold. So we'll make both OHs bold. Then we can, now we have some precise stereochemistry, more details, and now we can determine R and S here. Boom, boom, boom. What was the second one? Bold? Okay, so this must have been bold, and the chlorine was dash, and we'll make the OH dash. dash dash, and then we could have one that's dashed full. Okay. The R and S is going to be the same as above, because if this was a chlorine, it would still be, oxygen is still top priority just like chlorine. So the R and S is the same as above. We can do that real quick again. Oxygen is 1. Carbon with oxygen is 2. Carbon with nothing on it would be 3. H in the back, so the low priority group is in the back. 1, 2, 3 clockwise, so this is R, correct? Well, then that's R, because that's the same projection. We haven't changed the backbone. That's S and S. Down here, oxygen's 1. Carbon with oxygen is 2. Carbon with nothing is 3. H in the back. What is this? They're both R. That means this is what? RS. I bet you a steak dinner, that's S. I mean, you could prove it, do it. But the backbone's the same, we just changed the projection. It should be S. This should be what? S? And this is what? SR. Okay, so we kind of cheated after we did the first one. All right, how many compounds do we have on the board? What's the maximum number you can have here? You got 2 chiral carbons. Well, these are chiral. What is chiral? That means you have 2 different forms, 2 different configurations. We showed it. We have an R configuration and an S configuration. Those are the 2 possibilities. We say the carbon is stereogenic. Because of the way the carbon is substituted here, it has stereochemistry possibilities. That carbon is not stereogenic. There's no stereochemistry there. There's 3 H's attached. You draw them however you want. Yes, they are tetrahedral, but it doesn't really matter. There's only one way to connect them. There's 2 different ways to connect things here. How many compounds on the board? Well, go back here. 2 chiral carbons. What's the maximum number of stereoisomers? 4. 2 to the n, 4. Okay, well there's 4. Could you draw a 5th one up there?
No.
I mean, what about RR? Well, it's already up there. What about DL? Well, DL's up there already also. Well, that's something different. No, question though, how many compounds are on the board? Up there were 4 compounds, yes. Here, there ain't 4 compounds on the board. Let's look at this. Okay. I reckon I usually don't try to keep the text up there. We can draw these in Fischer projections. I should make some more room here so we can just have everything there. Amazing how something works for 10 years and all of a sudden it didn't look right. It needs more room. Okay, Fischer projection, 2 chiral carbons. We're going to have 2 crosshairs, so we can do like this, yeah? With usually your alkyl chain, 1, 2, 3, 4, top, bottom. So we can call this A, B, C, and D. I'm going to put A at the top. I could put D at the top, but I'm going to put A at the top. And D at the bottom. Okay, these are methyl groups. D's down by the ground. So the ground here is here. Okay? These 2 carbons are vertical. Okay? All right, with carbon A going away, that's what this means. Carbon A going away, which side the OH on? Well, OH is coming towards you. It's coming towards you.
Wait, we're looking that way. I thought we were looking this way.
Because your feet are on the ground.
You want to look over here?
Well, your feet are supposed to be on the ground, so these are the ground.
Yeah, but my feet are on the ground.
They're supposed to be coming towards you in the book.
It doesn't
Yeah,
matter.
the problem
what
is A going away from me or towards me?
Towards you.
Yeah, so I'm not on the correct side, right? Good. Be over here. And if you're on the ground, that is, I'm laying like this. Okay? So I think it's good to, here you are looking through here. You're kind of hovering up here, the feet on the ground. With the A going away and the OH coming towards you guys, it's on my left. Correct. A going away, the OH is on the left. That means the undrawn H is on the right. This looks naked up here. That's a methyl. Okay, with methyl D going away, because that's what that means, which side's the OH on? Okay. Little man's over here. There's a problem though. D's coming towards the little man.
Go on the other side.
So I'm going to come over here and look through here. Feet on the ground. And I'm laying down here on the sofa looking through here. D's going away. With D going away, the OH is on my... With D going away, the OH is on the right. The undrawn H is on the other way. Methyl down here. Okay? There's that and a Fischer projection. This means something. We can determine R and S right here. Now we can cheat. We know it's R. But is it? OH is 1. Carbon with OH is 2. So we go 1, 2. Methyl's 3. How's the H here? It's forward. So it's counterclockwise, but the H is forward. So we change it to clockwise, R. Yeah, it's R. Of course it is. I mean, it's R. But you can also tell it from here. There we go. Okay, I did one from scratch. I'm going to draw the other 3 just cheating now. Because I can draw this one. What's the difference? The OH is not changed. So the OH is still over here. Well, this one has it. We got 2 of the same. Which one is this? Well, this is the A carbon. A is at the top. So this is this OH, right? And D is at the bottom. Right? This is D. So the third OH is the one that's changed. So the third OH, instead of on the right, is now over here. We draw in H's in the Fischer projection. We make these methyls. So that's that. We're kind of cheating, yes?
I have a question. On the first Fischer projection, you did it 1, 2, 3, it was going counterclockwise. Well, you know it's R, but you said H is 4, so you flip it and it's clockwise. Why do you flip it in the Fischer projection?
No. That's the same thing. 1, 2, 3, it's counterclockwise.
Yeah.
But the H is coming forward. That's what we said yesterday. You can just reverse your clockwise, counterclockwise.
If it's in the Fischer projection.
No, anytime. Let's do RS here. Okay, oxygen's 1, carbon with oxygen's 2, methyl's 3, clockwise, but the undrawn H is, the low priority group is forward, so we reverse clockwise to counterclockwise. Yes?
Okay.
Same thing here.
Oh, because that's on a forward group. Okay, I got it.
Let's see. Let's get this one up. Okay, methyl. This OH is here, and it's changed from there, so that means it's over here, right? And this OH is the same, so it's the same as this. Okay? You can do these from scratch if you want. I'm cheating here. Methyl. The OH is the same, that means it's on the right. This OH is different, that means it is also on the right, correct? There are the 4 in Fischer projections. 4 structures in Fischer projections. We can number 1, 2, 3, and 4. What's the relationship between 1 and 3?
Mirrors.
1 and 3, look at them. Are they mirroring?
Yes.
Yeah, you can see they're mirroring. If 1 looked in the mirror, would it see 3?
Yes.
Everybody see that? It's much easier to see the mirroring in the Fischer projection. They're mirror images, yes. But everything has a mirror image. Here's the question. Are they the same or different?
Different.
1 and 3 the same or different?
Different. You can't superimpose them.
Why can't you superimpose them?
Well, if I try to stack them on top of each other, it doesn't work out.
Okay, OH, let's make blue, like water. Methyl's going back. If the methyl's going back, I gotta disconnect. The methyl's going back. The bottom OH is over there. Top OH is over here, correct? There's that one on the board. You get the idea what the Fischer represents? Top and bottom going back. Yeah? Let's do the other one. Three. The methyl's going back. The top OH is on the right. This OH is over here. Methyl's going back. Methyl's going back. Are those mirroring?
Yes.
If this looked in the mirror, would it see the other one? Everybody see it's mirroring? See that? Yes. They're mirror images. Same or different? You want to try to stack them. Okay? Let's just make the methyls going back. Make these methyls going back. Okay? Stack them. Methyls are overlapping. Right? But the blues aren't. I mean, for them to the same, it's got to all line up, right? Hopefully you see that. Well, let's make the blues line up. We can do that by turning. There. Now the blues are lining up. But look, the blacks aren't. Because this black is going that way. To make it the same, I have to disconnect each and reconfigure at each carbon. Then it would be exactly like that. These will not overlap. They were not superimposed. So they're different. Now, how could we know that they're different before doing this? We could look for Waldo, right? Does this have a plane of symmetry? Can you cut right through here? Is that a plane of symmetry? No. OH mirroring H, that's not a plane of symmetry. What about right through here? There's only 2 ways for us to look at the introductory level. I didn't think about it, there's more. Now, what if you cut right through here? Does this side mirror that side? No. So, if you can't find a plane of symmetry, that tells you that the mirror image is going to be different. Okay? So, what is the relationship between 1 and 3? Yes. Okay? Enantiomers. I had one that was good, and I set it down. Right there. Enantiomers. There you go. What about optical activity of these two? What do you know about the optical activity? No, that would be just a receiving mixture. If you just had this, would it be optically active? If you just had this?
No.
You don't have enough information.
Do what?
You don't have enough information at that.
If all you had was, if you had 100% this, would it be optically active?
No.
Yes.
No. Because you have to have a different ratio of the enantiomers, right?
We may not have ever said this, but if I had 100% of that, which is a carbon molecule, would it be optically active?
Wait, maybe it will.
Yes.
Yes.
Carbon molecules will bend light.
Only if you have enough of each just one of them, are they not optically active?
Only if you have a 50-50 mix is it not optically active, because the way this bends light will be counteracted exactly by this one, because enantiomers rotate equal and opposite. So if this one rotates 28 degrees positive, that one will rotate 28 degrees negative, and you'll end up back at the 0 point. 50-50 mix? Yes. How compounds are optically active? And we don't know to what extent. We have to do the experiment. Okay. But we know that, for example, if this one ended up being positive 25, what would that one be? If you had each pure. Negative. And positive, would that be D or L? D. So you can call this one D. Now look, this is RR. But what's D?
The whole thing.
The whole thing. D and L refers to the whole thing. It's not a specific carbon. Okay? It's that. So if that's D, what is this one? L. Now let me ask you this. Would you agree that that's a DL pair?
Yes.
Yeah. A pair of enantiomers is often called a DL pair. Because one will rotate light one way and one will rotate light the other way. There you go. That's a DL pair. I don't know which is D and which is L. I don't have enough information, but one's one, one's the other. Okay, what's the relationship between 1 and 2? By the way, I'm using a resonance arrow here. This is not a official use of resonance arrows.
Diastereomers?
We're not doing resonance, okay? Diastereomers. Why do you say they're diastereomers?
Because they're not the same, and they're not mirror images.
They're not mirror images. Because the mirror image of 201, I should have two OHs here. By the way, is this a rethrow or 3O? We may have to come back and clarify that. Yes, it is a rethrow until we say so. This one over here? 3O, yeah. The mirror image of a rethrow is a rethrow. Just like the mirror image of cis. These two groups are cis. You see my mirror image? Oh, you're also cis. The mirror image of cis is cis. Mirror image of trans is trans. Yes. Are these enantiomers? No, they're not mirror images. So clearly they're not. Are they stereoisomers?
Yes.
Yeah, they have the same connectivity. They have the same exact name. Both of these are 2,3-dihydroxybutane. All these up here are. Same exact connectivity, so if they're not enantiomers, but they are stereoisomers, what are they? Diastereomers. Diastereomers is kind of a default category. They're not enantiomers. Okay, here's the thing about diastereomers. Diastereomers have totally different properties. Enantiomers have same melting point, same density, etc., same polarity. Diastereomers totally different. Because of the positioning of these OHs, totally different properties. That should be written somewhere. They may have melting point difference of 100 degrees. Okay. What's the relationship between 2 and 4? Between 2 and 4.
Yeah.
What's the relationship between 2 and 4?
Waldo.
Are they mirror images?
No.
Yes. 2 and 4 are mirror images, yes. You see them mirroring?
No.
Does that mean they're different?
No.
No. Does not mean they're different. Here's the mirror image of this. Are they different? No, they're the same. 2 and 4 are mirror images. Are they the same or different? Well, how can we tell? We can make models and superimpose them. And we have 2. Nothing's going back. OHs are both on the same side here. It's like it's a rethrow. Yeah, that's that one. Okay. Let's do this one. Methyls going back. OHs are both on the right. There's that one on the board. Okay. Are they mirroring each other? I can make it straight here. Are they mirroring? Yes. Okay, same or different?
Same.
Same.
Or can they superimpose?
Yes.
Use flip one.
The blues are not lining up. Flip what? This one?
No, like take the whole thing.
Like this?
No.
Like that?
Put it backwards.
Yeah.
There you go.
Oh, look at there. Are they the same?
Yes.
That's the same exact compound. These aren't enantiomers. These are the same compound. Mirror images that are the same. If that's the same compound, how many compounds do I have drawn on the board? 3. That's only 3 compounds on the board. I just drew 2 twice. Turned it around. How do we know that the mirror image was going to be the same thing without superimposing them? We can look for Waldo. Do you see a plane of symmetry here? Ah, it's very nice. Look at there. See that plane of symmetry? It's easy to see in the Fischer. Since there's a plane of symmetry, it tells us the mirror image is the same thing. You have to trust that. So, is this a DL pair? Are these enantiomers? No, that's the same compound. Okay, this compound is called meso. Meso. Meso is a specific type of erythro. You see, you said earlier you said erythro. I'm like, well, kind of. We're going to eventually call it meso. It's more specific. What does meso mean? Meso is a compound that has chiral carbons. This compound has 2 chiral carbons. Yet the compound as a whole is not chiral. Even though it has chiral carbons, the mirror image is the same thing. Here's a take home. If a compound has 1 chiral carbon, it's going to always be chiral. If it has 2, it may not always be chiral. You can have the so-called meso. Now, also, you can have this with 3 or 4 or more. Ultimately, to tell if it's chiral, you want to ask where's Waldo. That's the ultimate we can take it back. We found Waldo right here. Okay, it's called meso. Okay, free information. Don't tell anybody I ever told you this. In meso, since that's a plane of symmetry, if that's R, that's going to be S. Why? Because the top is mirroring the bottom. What's the mirror of R?
S.
S. Since this is RR, you know it ain't meso. That ain't a mirror plane, because if R, looking in the mirror and seeing R, no. The mirror image of R is S. So that's a little trick. RS. Over here, this is probably SR. Yeah, you see? S is mirroring R. There's a mirror plane here. Now, of course, if we change this to bromine or something, that's still SR, but that don't mean they're mirroring. Because you have to have the same things to mirror. So of course that ain't. But here we have the possibility. But RR is not a mirror. Okay, so here we can have meso. The maximum possible is 4, but we really only have 3 compounds in this case. We have 1 DL pair, and then we have just a meso compound. For a total of 3. Questions? It's kind of a repeat of what we did above, except we threw in the idea of a meso compound, drawing Fischer projections, etc., etc. Okay, there's some things there to read. I'm not going to read them to you. By the way, reading, I would recommend
read the lab report requirements. That's all I can say. If you have questions about them, please ask. I don't tend to like to read things to you because I like to spend time working problems, etc. Question, let's move down here. How many chiral carbons does the following glaucoma drug contain? You want to have that answer?
Five?
I said 5? Who said 5?
I said five.
5?
I got 4.
We got 4.
Mm.
Got 4? How many chiral carbons? Okay. Let's see. That looks like a chiral carbon. This looks like a chiral carbon. That looks like a chiral carbon. That looks like a one. And one there. Are those all chiral?
Yes.
That is, would each carbon have 2 different projections, an R configuration and an S configuration that you could draw? Did we miss any? So the answer looks like 5. Who said 4? Which one did you miss?
The one on the top right.
That one? That's chiral, right? 4 different things. There's also an undropped H there. Yeah? How many stereogenic centers does it contain? A chiral carbon is only one type of stereogenic center. What other type do you know of?
Alkyne.
Yes, an alkene can be stereogenic. Is this alkene stereogenic?
Yes.
Yes. Why is it stereogenic? What does this mean?
Trans.
It can be
Trans or cis.
2 different configurations. Now, when we talk about an alkene, we're talking about the whole thing, 2-carbon alkene. The 2-carbon alkene can be either cis or trans. There it's trans. Could that be cis? Yeah. So we have 2 possibilities. Now here it's drawn as trans, but we could have also drawn it as cis. Here, these are drawn just generically. That's neither R or S. It's just drawn very generically. Is this, so that's stereogenic. Is this alkene stereogenic? There it's cis. Could it also be trans?
Yes.
Yes, it could. What about these in this benzene ring?
No.
No. I mean, here, this double bond is cis. Could that double bond be trans and still be in a ring? No. The pi bonds in a benzene ring are not stereogenic. Most rings not. If the ring becomes real big, you can have a trans double bond in a real big ring. I mean, you could have something. I mean, that looks ugly, but there's a ring with a trans. See, it has to be a big ring. Then the alkene can become stereogenic, and it can be both. But not in small rings like 6 or certainly smaller. They can't be trans. There's no way I'm going to make a ring with you guys. Would make a ring if I'm like this. You're going to say, "Hey, come on, move your hand over here." Right? Okay, so there we go. The answer there was 7, right? Because we have 2 stereogenic alkenes. Actually, none of the alkenes are non-stereogenic. How many stereoisomers are possible for this drug molecule?
So, 2 is 7?
How many stereoisomers?
Why isn't the carbon that has the oxygen bonded to it, why is it not chiral?
This one here?
Yes.
What's the geometry of that carbon? Planar. Something that's planar has plane symmetry.
So 2 to the 7th, right?
2 to the 7? Yeah. What's 2 to the 7? The answer is 2 to the 7. 2 to the 7
That's the,
equals what?
to the end. And
128? 128? Yeah, 128. Okay.
Whoever figured that many out must have.
Well, I mean, draw them all. Draw them all.
No.
Okay. How would you do it? You would go through. I mean, here's one. I can make all chirocarbons R and make both alkenes trans. That would be one. Then I can have all chirocarbons R and I can make both alkenes cis. That would be 2. But it's just all those variations. I can have four chirocarbons R, 1 chirocarbon S, 1 alkene cis, and the other one trans. That would be 1. You see? You keep going, you'll get 128. It's just math. This formula works. With N being the number of stereogenic sites. See, we included 2 because, yes, you have 2 you can draw for that, RS, but you also have 2 you can draw for this, cis or trans.
You gotta figure out which ones are.
Okay? Of the 68, I'll tell you this. You'll have 64, I'm sorry, of the 128, 64 will be DL pairs. 64 will be mirror images and enantiomers of each other. All right? It's all there. Will any of them be meso? Do you think so? Meso, you have to have a plane of symmetry. Where potentially? If you, I mean, it has to have a plane of symmetry, you have to have the same thing on each side. I mean, when we drew the alcohol, you can kind of see, this could be the same as this, as long as we got the right projections. Where could one side be the same as the other?
Nowhere.
You're not going to have a meso. You got to have some, you know, you'd have to have this up here, and it'd have to be also the same. You know, none of them's going to be meso. There'll be 128 total. All right. There we go. Diastereomers. We already defined it. Stereoisomers that are not mirror images. They have different physical properties. Epimers. What's an epimer? An epimer is a stereoisomer that differ by having only one center reversed. Let's look at the handout for carbohydrates. It's in the white. Yeah. Things here, we might look at some of the white. Get back here first. When you get to biochem and you look at your carbohydrates, you will show them in Fischer projections. And you'll be expected to know all about the Fischer projections. Now the carbohydrates have 1, 2, 3, 4 chirocarbons. And so we have 4 crosshairs. You see this? Isn't that beautiful? These are all stereoisomers. Now the one you may be familiar with is glucose. That's that one. Okay? Let's look at these. Allose. By the way, the D, capital DL is different from little dl. We're only dealing with little dl. If you want to know what capital DL is, it may be written here somewhere, but it's different than little dl. Okay. Question. Which one of these is an enantiomer of allose?
Wait, that's little d?
That's a capital D.
Oh.
It's written small, but it's a capital D. It doesn't mean the same thing as a lowercase d.
Because it's like based on the penultimate carbon, right? Like the first one is what defines that, whether it's D or L, those kind of compounds.
You're on the right track. Yeah, we're not going to be doing that here. Where'd you do that? Biology or?
I was just talking with one of my friends and he was telling me about it. It's biochem. So
Okay.
we're going to work together.
Okay. Yeah, in all of these, what's consistent is the stereochemistry at this carbon here. See, the OH is on the right in every one. That's why they're all D. It's convoluted a little bit. Okay. Which one's an enantiomer of this? What would the enantiomer look like? Mirror image. We should have one. If we drew a mirror here, the OHs would be
All on the left side.
on the left. Is there one up there with all of them on the left?
No.
Yeah, none of them are enantiomers. Actually, there's no enantiomer of anyone up here. All of these, or none of these are enantiomers of each other. What's the relationship between allose and altrose?
Diastereomers.
Good, they're diastereomers. How do you know that?
Because they're not mirror images.
Because they're not mirror images. Are they stereoisomers?
Yeah.
Yes.
Yeah, all these are stereoisomers. They all have the same connectivity, the same exact name if you give them. Yeah. These are stereoisomers that are not mirror images. These are diastereomers. All of these are diastereomers of each other. Okay? But these two are also known as epimers. What's the definition of an epimer?
Only one group is changed.
Only one group has changed. Isn't that right? Only one group has changed when you have multiple. So you can call these two epimers of each other. What about glucose? Is glucose an epimer of allose?
Yeah.
Yes. Only one has changed compared to this. What about mannose? Is mannose an epimer of allose?
No.
Mannose, more than one has changed. So mannose is a diastereomer of allose, but it's not an epimer.
Would mannose be an epimer of altrose?
Yeah, because only one thing has changed. Going from here to here, we only changed
Yeah.
the second carbon. Huh. Could we clarify this and say it's a, that's one,
It's a third carbon epimer.
how about a C3 epimer? We can give it some clarity. Altrose is a C3 epimer of mannose. You see how they're doing this? They're telling you. How do you see it written there? They're telling you, so, okay, so we can use that. Which has changed? C2 or C3? The one carbon, it should be probably the carbonyl. Okay, so there you go. You're going to see some Fischer projections there. Ultimately, let's look up here. This is kind of the starting of getting to be carbohydrates. That is a carbohydrate. What's a carbohydrate, by the way? All of these have this formula. They have carbon with some number of water in the formula. So it's a carbon and water, carbohydrate. That's the formula of all of them. For example, what's the formula of this? How many carbons? C3? Is that right?
Yes.
Okay. It's going to have 3 waters. H2O3. That's the formula. It should have 3 oxygens, does it? Yes. If it has H2 times, it should have 6 H's. Does it? 1, 2, 3, 4, 5, 6. You see? It's carbon and then a corresponding number of waters. They all have that formula. That's why they're called carbohydrates. That's a C3 carbohydrate. These are C6 carbohydrates down the road. Look at these guys though. This is a C4 carbohydrate. When the OHs are on the same side, it's called erythrose.
The OHs are on opposite side, it's called threos. Where have you heard that before? That's where the erythro-threo terminology comes from. Okay, anything else? Let's look at something here. We can look at miscellaneous one. Here's a drug. Anybody ever heard of levofloxacin? Brand name is Levaquin. Anybody ever heard of this? Yeah? What do you know about it?
Is it a blood thinner? Is
What
Levaquin?
type of drug is it?
Is it a blood thinner?
No, it's a antibiotic. Yeah?
Oh, yeah.
It's sort of I will never take this. It'll ruin your hearing. It'll ruin your tendons. It's got bad side effects. Be careful. It's a fluoroquinolone. Quinolone. This is a quinolone. It's got fluorine. It's called fluoroquinolone. Lots of these. Ofloxacin, ciprofloxacin. I've shown you some cipro before. Yeah. It's given as a hemihydrate. What's hemi mean? Half. Okay. It's a half of a water molecule associated with each of these molecules. That's the drug form. So the molecular weight includes a half a mole of water. Okay. Is it R or S? How many carbons does it have? Just one, and it's right here. And it's shown in a very specific, because it is, if you take this drug, you get one very specific orientation or configuration. Is it R or S? What's high priority group on this carbon?
Nitrogen?
Nitrogen, carbon, or carbon?
So the nitrogen.
Nitrogen 1. This oxygen is not bonded to this. Carbon's bonded to it. We only look out here if we have a tie. For example, here we have a tie. Which is best, carbon or carbon?
The one on the left bonded to oxygen.
We have to then look at what's bonded to it. This is bonded to 3 H's. Okay? H, H, H. This is bonded to O, H, H. Well, right here you get a winner. O beats H. So this is 2. That's 2. Methyl's 3. H is the low priority group 4. It's in the back. So what is this?
S.
S? Yeah. It's the S configuration. It's the one that's given as the drug. The R configuration, I don't know, it may be toxic. That's toxic there. It may be inactive. I don't know. Yeah, it's an antibiotic. Okay, is it D or L?
No. Give me more information, please.
D or L? What information do you need?
Need the PP, whatever
The
that
direction
test
of
is.
rotation.
Yeah, the optical direction.
Yeah, but what's the name of this compound?
Levaquin, it's got an L.
Levofloxacin. Why do you think they called it levofloxacin?
It's L.
Huh? A lot of times names will give you information. Yes, just looking at structure you can tell. But since they called it levofloxacin, guess what? It's L. That's why they called it levofloxacin. And not dextrofloxacin. Or what, okay? A lot of times names will tell you some information. It's actually L. The only way you can tell that there is from believing that that's why they named it. You can't tell from the structure. Right? Anything else you want to look at in here? We can come back at some point. Daily questions? Any questions there? We'll take a 2-minute break. I'm going to pass back lab reports for the Tuesday, Thursday group. And when we start back up, I'll see if you have any questions here. If not, we're going to be moving on to alkyne chemistry. The alkyne handout. Okay, guys, 2-minute break. If you want to pick it up here, please yell. Karina.
Here.
Including the other group, the grades labs range from 10 out of 10 to I think 4 out of 10. That's including both groups. I'll make some comments in a little bit. Karina. Jennifer.
Yes.
Thomas Stringer. Julia.
Here.
Remy. Is that right?
Yes.
Matthew Stolfus. Esther.
Here.
Caesar.
Here.
Kayla.
Here.
Troy. Alexandra.
Here.
Victoria.
Here.
Jacqueline.
Here.
Taylor.
Here.
Jake. Nick. Lauren. Bianca. Catherine.
Here. But then I was worried because like some of these peaks, like I don't know if I should worry about these peaks. Because I feel like they might be showing like a CO bond or something. So don't worry about them. Okay. Never mind.
There should be, you should consider all relevant peaks.
I don't have that.
Is anybody else missing the lab from the lab manual? Something happened here?
It was like halfway out and I pressed it. I'll flip through all the other pages to see if it was
Come by now.
What's the name of the lab again? What's the name of the lab that we're looking for? I'm sorry.
page 39.
Okay, guys, we'll get started. Lab reports, first off. Need to make sure that when you discuss things, one of the major things for me is you explain, give a full explanation, strive for clarity. I'll say this perhaps again, but it's like if I ask you why is Bill Gates rich? Explain to me why Bill Gates is rich. You should not just say because he has lots of money. That's really not an answer. Then I'll have to say, okay, well, why does he have lots of money? So a deeper explanation of not just sort of restating things. Okay, that's a very general statement. In general, you guys didn't really discuss the acid-base chemistry that well. A couple of you did, yeah. Not explaining why things precipitated. It precipitated because it reacted with the acid. It doesn't explain why it precipitated, because you could have things react with acids that don't precipitate. Many of you had trouble drawing acid-base reactions. Many of you tried to react sodium saccharin with sodium hydroxide. It's just not acidic. There's no proton there. There's no reaction. The only reason it dissolved in sodium hydroxide is because it's just aqueous. Many of you just didn't explain why sodium saccharin didn't dissolve in sulfuric acid. Okay, I could go on and on. There's a number of things. I made notes. Here's the thing. If you need more explanation, please ask me. I don't write a lot of explanation. I do a lot of just question marks. If you see a question mark, it means I don't understand what you're saying here. It doesn't make sense. That's what the question mark means. I would recommend that you look at that and say, okay, why doesn't it make sense to the instructor? How could I have rephrased it better? What did I miss? That way you will then not make the same mistakes. I'll be happy to sit down with you and go through your lab report and give you more details, explanations, etc. There are specific guidelines, for example, putting your name on the back. So we can return them up front. Okay. There's other specific guidelines, such as reference format. I'm not sure that you read that part. Please look at the guidelines. The guidelines are there because they're important, and they cover every detail of the expectations for the lab report. If the guidelines are not clear, please ask. Okay, guys, let's pick up with alkyne reactions. Alkyne. Okay, we're moving through kind of to the home stretch here. Okay. Test Monday. I said I would ask about last questions of stereochemistry. Last question of stereochemistry before we leave them. Okay, let's start with alkynes. Here's an overview of alkynes. We have 2 pi bonds, so like I said, it's going to be twice the fun. We'll see lots of consistencies. We're going to see same reagents. Okay, in some cases we'll just do the reaction twice because there's 2 pi bonds. All right, so it's not like it's going to be all brand new stuff. For example, we'll react an alkyne with HX, like HBr. We'll add HBr across the pi bond. Where are we going to make cation at, left or right? Correct, on the left, because it'd be a more substituted cation. It's going to be the same idea. And so if cation's there, that's where the X is going to bond. That's why the X is on that carbon. Okay? But guess what? That's an alkene. The product is an alkene. It can react again with HX. And so you can have twice the fun. All right? We'll refer back to this as we go along. Make some comments here. We'll hydrate alkynes. This will be a little bit different because when you hydrate, you only hydrate once. Then this will actually undergo a rearrangement called a tautomerization, and we'll get a carbonyl. So you only hydrate one time. We'll have to learn about the rearrangement called tautomerization. Okay? We can hydrogenate alkynes. You can actually do it twice. Add 2 H's to get an alkene. Add 2 more H's to get the alkane. But you can just add once using a poison catalyst. Now when you add once, you get an alkene. It'll be cis here because we know the H's come from the same side. 2 darts. You know, right? Everybody else following the 2 darts coming in? Yeah? Well then, can you make a transalkene? Yeah, but it's different reagents. Okay? So that's hydrogenation. This is totally different new reagents. All right. There's some drugs with alkenes and alkynes. There's an antifungal. Which one? 18 looks like an antifungal. Yeah, down here. What's 18? Lamisil. You've heard of seen commercials with Lamisil, right? Something. Antifungal. So you can see okay, we'll start with nomenclature. We'll do that here. It's not on the video. Video just covered the alkene nomenclature, including the EZ nomenclature. This idea of alkenes being stereogenic, or possibly stereogenic. An alkyne is not stereogenic. Okay? You cannot have cis or trans without the triple bond because the groups are not like this. They're linear. And if they're linear, they can't be cis or trans. So alkynes are not stereogenic. Terminal versus internal. When the alkyne's on the end of the chain, and thus there's an H bonded to the alkyne carbon, like this, that's called a terminal alkyne. If the alkyne's in the middle of your chain, that is with no H bonded to the carbon, that's called an internal alkyne. Okay? Should be pretty straightforward. Now, a lot of times I will draw in the H, but not always. Okay? You know, this could just be drawn boom, 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 like that. Try that again. Boom, 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 like that. A lot of times students lose track of the carbons here because it's linear. 1, 2, 3, 4, 5. Okay? A lot of times students will draw 1, 2, 3, 4, 5. But that's a horrendous bond angle because this carbon here is supposed to be linear. Okay? So that's really kind of amateur-like. Okay? So I'm drawing it linear because that's the way it is. But don't lose track of that carbon there because you don't have the zigzag line. Okay? Nomenclature. Just like with alkanes and alkenes, it's all going to be similar as you go through organic 1 and 2. Longest continuous chain. What do we got here? 1, 2, 3, 4, 5. It's only one chain. It's 5. So it's what? Kent? Well, we indicate the functional group or that's there with the ending, so it's pent Not ain, not een, but ein, pentyne. Okay? But if that's pentyne, then what is that? This is also pentyne. But the name is not sufficient because we indicate, just like with alkenes, where the triple bond's at. Denoting the first carbon that it's at, where's it at? 1, because this is 1, 2, 3, 4, 5. We only write them 1. That's where the triple bond begins. Just like alkenes, yeah? What is this guy? 1, 2, 3 pentyne?
No, 2.
No, what is it?
2.
2 pentyne, because you come from over here.
There's no such thing as 3 pentyne.
3 pentyne is somebody I know, it's garbage. It's nonsense. You cannot have 3 pentyne. Okay, there you go. So those would be constitutional isomers. Name the other compound up there. Somebody got it? Yeah, it looks like it's 3 heptine. Do we need a stereochemical descriptor or anything? No, there's no stereochemistry there. There's nothing there is stereogenic. Okay, pretty basic. Yeah? If there was a chlorine here, what would it be? Is that a chlorine there? What would that be?
6 chloro, 3
Be 6 chloro. 3 heptine. Or would it be 2 chloro, 4 heptine?
2 chloro, 4 heptine.
No, because you're never going to put the...
No, the main functional group takes priority. 3 heptine. It's like with alkene. Look on the alkene handout, it's probably going to say somewhere the alkene takes priority. Okay. Reactions, electrophilic additions, just as with alkenes, except a few additional considerations. You take this terminal alkyne, react with HCl, we can get this product. Very similar. We got H plus Cl minus. You show it ionic or do it covalent. Pi electrons attack. Are we going to leave cation on the left or right? Correct. We leave it on the left. And we'll get boom, boom, boom. Okay, now how are we going to draw this? It's 1, 2, 3, 5 carbons. 1, 2, 3, 4, 5 carbons. I can draw it like this now. Which carbon is bonded to the H, the left or the right one? The right one, because we're leaving cation on the left one. So the right one, which is the 5th one, has a bond to H. It's also still an alkene. We only use 1 pi bond. There's triple. We made a bond to that H. There's actually 2 H's here now, right? There's 1 there to begin with. There's now 2. Only drawing the new one. And this is a plus charge. Now, this is a bad positive on an alkene. This is worse than like the primary carbocation. Some books will discuss how this is bad, and blah, et cetera, et cetera. But I don't think it's worth discussing. You should know the hybridization of this carbocation. And if you think about the hybridization, you will see that my bond angle is actually wrong. What's the hybridization of the carbocation?
SP2 planar. SP2 planar. 1, 2.
SP2?
Oh, SP.
There's only 2 groups here. There's no H. Double bond, single bond.
Yes, it's linear.
SP linear.
Yeah.
He's actually still linear.
Yeah.
Actually is. But I went ahead and did this. Because ultimately I know we're going to get to that. What's next? And the electrons come in here, on here, and there we go. Now it's sp2 trigonal planar, and the bond angle is more appropriate as I drew it. Okay? Anything new there? We do have an alkene left though, because we only reacted one. This would be a potential product. Well, this is an alkene. It can react again with HCl. Okay? If it reacts, where are we going to leave cation? Left or right? Correct, on the left. Even with the chlorine there? Well, let's look at that. H plus Cl minus. Pull these away from that carbon, tack there, and that's going to give boom, 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 boom. Chlorine, new H there, positive here. We're just doing it again. Okay? How do you like that cation? Secondary. That's not a carbon. This is bonded to two carbons. Secondary.
Yeah, chlorine can take some of that charge. though.
Ultimately, can we see how we get this? The other chlorine is going to come in. We're going to get two chlorines on the same carbon. Yes. But let's look at this. What do you think about the stability of that cation?
Resonance, right? I mean, that chlorine is.
Or would you have rather have formed UH here and cation out there?
No, because the secondary is still going to be more stable.
That is, would you rather have pulled it away, made bond here, and left that cation?
No.
That's on a primary carbon.
Yes, that's primary. Yes, secondary is better. That is right. And that gives us the answer. But tell me about the chlorine. Is the chlorine, what's it, is it helping or hurting?
It's pulling some of that charge away. Spreading
It
the
pulls
charge.
how?
It's got electrons.
Well, no.
This way.
Yeah.
What's the terminology for pulling this way?
Electronic withdrawal. Exactly.
Induction. It pulls
Induction.
inductively. That's single bond, right? It pulls inductively due to electronegativity. So is that going to stabilize it?
Yes.
No. If you're electron poor and I pull money away from you, does that help you?
Oh, no.
No. Inductive withdrawal is not a good thing. But there's another way that the chlorine could operate, or something else it could do. It can donate by resonance. That is, if we were drawing this on day one, and we said this carbon needs to make a bond, didn't we take electrons next door and say, hey, make bond? This is resonance. And this is a resonance arrow. And we get boom, 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 boom. Double bond to chlorine. And the chlorine has a positive charge. There's new H here. This may look bad. You're like, well, that chlorine has a positive. Chlorine's very electronegative. Why would it want positive? It's okay. This is common. The good news is chlorine has an octet. The good news is we just made another bond. And bonding is good. This outweighs the withdrawal. You could still make an argument. What you have here is a resonance stabilized carbocation. Stabilized by resonance. And we can draw an alternative Lewis structure where all we did is move pi electrons. One of these lone pairs is an p orbital, right? Right. This is the reason why it's stabilized. We'll talk about this more. Another explanation for why it's stabilized, the true structure is what? It's actually somewhere in between these two. The True structure is not a single bond here, not a double bond, but somewhere in between. Boom, 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 boom. Sort of a bond and a half. The true structure is not a plus on carbon, not a neutral, but a partial plus. Same here. Not a neutral, not a plus, but a partial plus. If you could actually see the compound, it would look like this. Partial bonding here. By the way, this almost looks like back bonding. But we don't call it back bonding here because we're not making a new sigma bond. These are fake. We'll talk more about them. Here's your true structure, but that's cumbersome. The main thing is the charge is not sitting directly on the carbon. Some of the positive has been delocalized onto the chlorine. And if you can spread the charge out, that's a good thing. Ultimately, this is a resonance stabilized cation. Yes, you could have gotten the answer by just saying that's secondary versus primary. But there's more to it here that you need to kind of start understanding. You got resonance here. Okay, once we get that, the final is home free. Boom, you attack the cation, and you get the product. Now you can always work with any resonance structure. We could have worked with this one. Over here, you attack here and you push these up. That gives the product also. You can always work with any resonance structure. Don't let anybody tell you you can't. So, if we add twice to this alkyne, what type of product do we get? Say geminal dihalide, geminal dichloride. Twins, right? On the same carbon? All right.
Do we have to keep showing the age that we bonded in the first time since we're not showing any of the other ages? I mean, I know it's because we bonded, but sometimes it's
No?
Do you want us to show the step where the charge is delocalized?
A resonance?
Yeah, the resonance step.
Well, not necessarily. Unless the question said, show all resonance for any intermediates where it's applicable.
Okay.
It's called a vinyl cation. Double bond is often called vinyl. The cation's on the double bonded carbon. That's the vinyl term. A lot of times this is called vinyl chloride. And if you polymerize vinyl chloride, you get what? Polyvinyl chloride, which is what? PVC. It's amazing, right? That's vinyl. Okay, what's down here? About reaction with halogen, like chlorine or bromine. React this alkyne with bromine. We're going to get a very similar outcome as alkenes. We're going to get a bromine on each carbon. Alkene will remain there because we only react one pi bond. This will be E though, right? Why not Z? Why will the bromines be opposite? There's one intermediate here. What's it going to look like? It's actually going to look kind of ugly. It's going to look like this. Here's your one intermediate. Right? How did we get there?
The first bromine back
There's a
bonded.
bromine, it's schizophrenic. One bromine becomes positive. Where are we going to leave cation, right or left?
Left.
Left. So this attacks, kicks that off. It's always covalent, yeah? By the way, we're using BR2 today in lab, yeah? What does that give? Boom, boom, boom. 4, let's see, 5. Now we have a bromine here. Double bond still there. We reacted the 1 pi bond and a positive charge. Okay. Is this going to exist or what?
No.
This is going to back bond. That's NaF. And when it back bonds, what do you get? You get that. Right? I mean, so that was it. What's the next step? Which carbon are you going to attack, left or right? The answer is the same as this. Right? Correct? This comes in. How? How does it come in?
In the opposite
We're
direction.
kicking something off. Comes in here. Okay? So does it make sense that these VRs are opposite of yeah? That one's going to be up, this one's going to be down. That's fixed. There's no free rotation here. There you go. It's going to be like that, right? Okay, but this is an alkene. Alkenes can react with bromine, so you can do it again. If you did it again, you'd get that product down there. And this product has no stereochemistry. Is there any stereochemistry we can show here?
All free rotation.
How many chiral carbons? How many stereogenic sites here?
None.
There's no stereochemistry. As long as you have everything connected, fine. Yes, that's tetrahedral. Yes, one's forward, one's back, but however you want to draw it. Usually we just draw that generically. Okay, anything really new there? You can do it twice. You do need to know what the sort of, after you do it once, looks like. Questions? Okay, hydration. We can add water to the pi bond, usually with an H+ catalyst. We can also do oxymercuration, things like that. Hydroboration, oxidation. With alkynes, you typically sort of combine like aqueous acid and also include the mercury. Like mercury acetate. Often combined. All right, historically just combined here. When I do the mechanism, I'm not going to use the mercury. I'm just going to do it as if it's just H3O+, which you may see mercury included. When you first hydrate the alkyne, you get this. There's a new H there, right? One H on the end. There's now two on the end. So there's a new H. There's your water, H2O, added across the pi bond. This is an alcohol, but it's got a special name, a special type of alcohol. It's called an enol. Enol. Because it's an alkene that has an ol on it, an OH on it. So it's an alkene with an alcohol on it. And it's called an enol. All right? Now you may be familiar with like a donkey. What does a donkey say? Enol. You ever heard a donkey? Something like that? Look it up on the YouTube. Donkey making noise. Sounds like enol. He's saying enol, enol. Okay? That's an enol. Now the enol you don't hydrate again, so you don't have twice the fun. Instead, the enol will undergo a rearrangement. And it will give you, in this particular case, this ketone. It will rearrange to a carbonyl. Same formula. That's just a rearrangement. So we haven't hydrated again. Same exact formula. This process is called a tautomerization. These two constitutional isomers, in the context of this reaction, are called tautomers. Definition of a tautomer is, I believe, written below. Or above. A tautomer involves relocation of a single hydrogen and relocation of at least one pi bond. So you only relocate one atom, one H is relocated, but then you also move a pi bond. Is that what has happened here? Well, the oxygen has an H, it's now gone. So it looks like this H has been moved. Where's it been moved to? Can you find that? 2 H's here? How many there now? 3. Yes, there's the H that's been relocated. Has any other atom been moved? The answer is no. Just the pi bond, which was the other part of the definition of the tautomer. We also relocated the pi bond. Instead of between the 2 carbons, it's now between carbon and oxygen. So, there's your definition of tautomers. Those are tautomers, and the process is called tautomerization. Now, if you relocate 2 H's, are those tautomers? No, those would not be called tautomers. Now, you could relocate more than one pi bond. It could be 1 H and 3 pi bonds. Those could be tautomers. Okay. Mechanism. Well, we're going to forget the mercury, okay? It just may be there. Just do it as if it's just aqueous acid. H plus in water. Pi bond attacks. We're going to leave cation on left or right. Correct. So we get here, boom, boom, boom. I'm going to go ahead and do it like this. Was triple, now it's that, and we made a new H. Okay. Now you got to see what we're doing here. Now there's one drone in there. It almost looks like that's there. There's 2 there now. I may do it different ways. You can tell how many H's are there by looking at the carbon counting the bonds and if there's a charge or not. Okay. 1 there originally, now there's 2. Plus charge here. Does anything back bond?
No.
So do you think this is actually formed?
Yes.
Yes, it's actually formed. This is a carbocation reaction. There's nothing to back bond. And it's not going to be any fancy hydride shift or anything. This is a good old classical carbocation. Some people don't like vinyl cations, but we won't go into that. What adds to the cation?
Water.
Water, okay? Bam! These electrons add there. What does that give? Boom, boom, boom. Double bond. There's 2 H's there. What's here? O, H, H. 1 lone pair left, and that's a positive charge. By the way, now that we've spent several days on mechanisms, now please go back and look at the mechanism 2 pages in the first handout. I give you an overview of mechanisms. Now if you go back and reread it, it should make more sense. And you can look for the finer details. Okay? All right? For example, every time you move an arrow, you say in your mind what? These electrons. These electrons attack H. These electrons. Otherwise, you're going to end up with your arrows backwards and you're going to be losing points. Okay? How do we get from here to here? Something's got to take the H. What can take it? Well, there had to be a minus here.
Water.
Or you can use water. That's fine too. But there had to be a minus and you could have used it. For example, we could have just said sulfuric acid. Then you could have used sulfate. But since it's just shown generically, we'll just use water. Take the H. These electrons take the H. These electrons stay behind. We get that and we reform what? We reform the catalyst, which was the acid. There's acid again. There you go. There's your enol. But Now the enol is not stable. The brackets, when you see that, it's not isolated. Not isolated, it just continues on. Well, what's the mechanism in going from here to there?
Hydration.
You should be able to do it. We've seen every step already. Okay? I probably will ask you to do it on your own. We'll look at it tomorrow, see how you did. Let's see what's going on. First off, what's this reacting with? What's in the flask when this happens? This is all still, it's all that's still in this flask. It's still got acid around. This is in the same flask. So you still got H plus and water around. It's just going to continue to react. Okay. All right. How could this react? Well, we got an alkene. Have you ever seen an alkene react with H plus?
Yeah.
Go back yesterday and the day before, we did it plenty. Well, that's the first step. Where do you want to make cation at? Left or right? Correct. By the way, when you do that, where are you going to add, which carbon takes on an H? Left or right?
Right.
Carbon on the right. Isn't that the carbon that needs an H?
Yeah.
It's all going to fall into place if you use what we've been doing. It's really nothing new.
And then it leaves the cation right there. That oxygen's pissed off because he has an extra set of lone pair, and he's going to move on to that.
You already see it, right?
Yeah.
I didn't even have to show it to you. Do it on your own. Okay? It's a take-home quiz. We'll grade it first thing in the morning. All right? There's really nothing new in that mechanism. At some point, you want to take an H off of this oxygen, yeah? Have you ever taken H's off of oxygen?
Yeah.
We just did it right there. It's all there. Please give it a try. Okay, we're about out of time. Last questions for today. Question.
When we're doing like that kind of like hydration mechanism, do you want us to put like the acid reform, like if it's H3O plus or like H2SO4? Like, should we like say that at the end?
Not necessarily. You should know it.
Yeah, okay. I just never write it.
Yeah, not necessarily. But maybe the instructor asked you to, after your mechanism, answer this question. Was the acid in catalyst or not? Yes. You should know if it was or not. It's not always a catalyst. Okay, guys, see some of you this afternoon right here. Have a good day.